Now, let's talk about parallel hashing. You remember our hashing algorithm, right? With its two phases, the first in which we partition with the hash function HP, and the second in which we conquer by building a hash table in memory with a hash function HR for every partition. And we talked about how to parallelize this when we learned hashing. We put an additional phase out front of phase one where we shuffle data across machines using a hash function hn modulo the number of machines. And as data is scanned, it streams out to the network and is partitioned through the shuffling function. And so another hash function hn is used to do that. And then we proceed as we did before with our two phases of hashing locally on each machine, right? And this is almost exactly the same as single node hashing, so that's great. The only addition was this partitioning phase that shuffles. But the other thing to note is this is going to give us near perfect speed up and scale up. Think about this. In phase one, we're streaming data. Data streams through the shuffle, streams into the input buffers for partitioning, and streams to the disk on each node. So that whole pipeline through HN and HP is a streaming algorithm, which means that these disks and CPUs are working just as fast as the network can fill up their buffers with data. Right? And if everybody's working at about the same speed, then this will have very good utilization of all the hardware. All the hardware is going to be doing useful work at all times, and we're going to get perfect speed up and scale up. Okay? However, we can't start phase two until we finish phase one. So there could be a moment where some of the machines are done with phase one, and some of them are still working on it because maybe there was skew in our hash function and some machines had to deal with more tuples. And we can't start phase two until phase one is finished. And so that is a potential to limit our speed up and scale up somewhat to the speed of the smallest batch that works here, sometimes called a straggler. Okay, so we do have to wait in phase two for any stragglers from phase one. What about hash join now? We've looked at hash partitioning, but what about hash join? Well, it actually turns out to be pretty simple. If you have enough machines, we can do a naive parallel hash join. So let's go through that. In phase one, we're going to shuffle the tables across machines using HN, and we're going to build a hash table at each machine using HR. So we scan that first building table streaming out to the network. We wait till the building is finished, and then we stream the probing relation through shuffle and look for matches at each individual node. So receivers proceed with naive hashing in a pipeline as the probe data streams in from local disk and network. Note that the writes of the matches are independent. Every machine writes out its matching tuples independently, and so they run in parallel without any coordination across machines. So the only communication in this algorithm is to partition the input data by HN to the different nodes. First we partition the building relation, and then we stream through and partition the probing relation. Now in a few slides we're going to learn a variation that has no waiting between the building and probing phases. Both tables are going to stream simultaneously. It's called the symmetric or pipeline hash join, and it requires more memory space. And hold that thought, we'll learn about it in a few slides. Now let's talk about parallelizing Grace hash join for the cases where we don't have enough memory to use naive hash join on the local nodes. Pass 1 of Grace hash join is going to look a bit like pass 1 of naive hash join as we think about parallelism. Again, we're going to have every node locally scanning tuples and then shuffling them across the network by looking at each tuple, computing a hash function h sub n, and figuring out which destination machine will handle that tuple. Tuples will arrive at these machines into an input buffer, and then each machine locally will simply be doing pass 1 of Grace hash join as it did before, writing those tuples off to partitions using a hash function HP. The only change really from single node parallel partitioning is that we're going to do this for both relations in parallel Grace hash join, R and S. And we can either do those relations one at a time, or in fact we could do both relations simultaneously if we have enough output partition buffers. It really doesn't matter because in this first phase they're being written to separate partitions on disk. So if we have enough output buffers to do both relations at once, we can intermingle them in our messages on the network. And if not, we can do R first and then do S second. Now in pass 2 of Grace hash join, everything now is local to the individual machines. There's no more need to communicate. So these nodes are completely independent. Each one runs as fast as it can, doing a local Grace hash join for pass 2. So to summarize, pass 1 of parallel Grace hash join is parallel streaming. We're streaming the building and probing tables through shuffle and partition, and we're making good use of all of our hardware resources, CPUs, disks, and network buffers. We're doing that all in parallel with great utilization, so it should scale up and speed up perfectly. Pass 2 is simple local Grace hash join, complete independence. There's no need for these machines to even talk in Pass 2. So again, we should get great utilization out of each machine and get great speed up and scale up in Pass 2. So the whole business should be near perfect with speed up and scale up, every component working at its top speed. And the only time we wait in this context, where one machine waits for another machine, is we have to wait for Pass 1 to end. And so as we've discussed before, if there's any skew in the hash function, or if one of the machines slows down, then we may have stragglers in Pass 1 and we may wait for them in Pass 2. Note that as there was with naive, also with Grace hash join, there's been a variant invented that has no waiting. It's called the X join, and it's really a disk-based variant of symmetric hash join, which we're going to learn later.